Welcome to the third and final part of the video series of the unbalanced fault analysis. In this part of the video, we are going to look into the analysis of the unbalanced fault, which is the single line to ground fault, line to line fault, and also the double line to ground fault. And in the analysis of all these types of fault, we are going to apply the concept of symmetrical components and also the impact of the symmetrical components on transformer, Y balance load, and also the Y balance generator into their analysis. Okay, and now let's begin with the analysis of the single line to ground fault over here. And let's assume that the single line to ground fault now is striking a particular bus of a network and that we are zooming into that bus. And when we zoom into that bus, the three-phase circuit will look like this. And we further assume that the single line to ground fault is affecting phase A of the three-phase circuit. Therefore, we can connect phase A directly to the ground through the equivalent impedance of the fault. When we have a single line to ground fault affecting phase A, it will leave phase B and phase C open circuit, such as like this. So from our observations of this circuit, we notice that VA, that is the voltage drop in phase A, from this line to ground is given to us by IA multiplied by ZF, such as like this. And because we have a single line to ground short circuit fault from phase A to the ground, it will leave phase B and phase C open circuit, and IB and IC is therefore 0, such as like this. And in our previous videos, we know that the symmetrical current is related to the phase current through the multiplications of the inverse A matrix divided by 3. And because we established that IB and IC is 0, therefore we can write IB and IC here as 0. So from the simplifications of this matrix, we notice that IA 0 equals to IA1 equals to IA2 equals to IA over 3. And in our previous videos, we also know that VA is equals to the summations of all the VA of symmetrical components. And also in the analysis of our Y balance generator, we know that VA 0, 1, and 2 can be further expressed into this form. And we can substitute this into here and then simplify it, and we will get this form. And from this one, we can actually say that IA is equals to 3IA0, which can be further substituted inside here. And the result is that VA is equals to 3ZFIA0. And VA is also equals to this. Therefore, we can say that 3ZFIA0 is equals to this, such as like this. So we can go ahead and rearrange the equations by taking IA0 to one side of the equations and the remaining terms to the other side of the equations, and this is what we will obtain. And then knowing IA0, we also know what is IA1 and IA2, and we will automatically also know what is IA. And we don't have to bother about IB and IC because we have established that they are 0. And now the question comes, what if the single line to ground fault now is striking the other two phases instead of the phase A over here? Under that kind of condition, is the analysis still valid and is the equation still valid? The answer is yes. When we have the fault impedance connecting from any of the phases, we can simply rotate, the three-phase circuit until we have the impedance in these positions and also our phase that is affected by the fault in this position. And we can go ahead and call this phase as phase A, phase B, and phase C. All right. The reason we can do this is because the notations of phase A and B is just a matter of relativity. Okay. If you call this as phase A, then of course this is B and C in the positive sequence order. And if you take this and turn it over here, again, and as you take this turning over here, the other two will have to turn as well. Then this one will become phase A. Okay, if you take this and turn it over here, this will become phase A. So either phase A, B, or C, it is just a matter of relativity. And therefore, the question where the equation shown over here is still valid for that kind of condition, yes, the answer is yes. You can still use these derivations for the calculations of single line to ground fault that is affecting other phases. Next, we look into the line-to-line fault now. So in the line-to-line fault, we have two lines or two phases that is short-circuited through the fault impedance, leaving the other faults open circuit. So under these conditions, we observe that VB, which is from here to here, minus VC, which is from here to here, is equals to ZF multiply IB, such as this. And then we also observe that IB plus IC is equals to 0. And because this has become open circuit, we say that IA is equals to 0. And our symmetrical components analysis also says that the symmetrical current is related to the phase current as such. And because IA is 0, we write 0. IB is IB and IC is equals to negative IB from this relationship. And from this, we derive these three expressions. And from these two parallel equations, we can further express them into this form. That is, IA1 is equals to negative IA2. And this is the properties that we have established in our first part of the video series. That is that the phase voltage is equal to the summations of their respective phase voltage of all symmetrical components. And we know that VB minus VC is equal to ZFIB. And because we have this VB minus VC, instead of writing VB minus VC, we can write these expressions minus these expressions. And if we simplify the subtractions, it will look like this. And of course, this is equals to ZFIB. And we also know this from the analysis of the Y-balance generator. And we can go ahead and substitute the expressions of VA1 and VA2 into here and simplify them further. And this is what we will get. And then we can look into these equations and express IB in terms of IA1 and then substitute inside here. And then this is what we will get. Okay. And then we can go ahead and taking IA1 into the other side of the equations and the remaining terms into the other side of the equations. And this is the final form of the line-to-line fault equations that we will obtain. So knowing the value of IA1, we will automatically also know what is the value of IA2, which is the inverse of IA1. And IA0 is 0. And knowing the three symmetrical components, IA, 0, 1, and 2, we can go ahead and determine what is the value of phase A, B, and C by multiplying the phase the A matrix like this. So again, if the fault is now happening at phase A and phase B instead of phase B and phase C, is the equation derived here valid? Yes, the answer is yes. And the reason is similar to the previous analysis for the single line to ground fault, whereby you simply have to turn this three-phase circuit until this phase become this phase, and this phase become this phase, and this phase become this phase. All right. So as you turn this clockwise, when you have a short circuit, that is the line-to-line fault between phase A and B, you just have to turn it until you get this arrangement again. Then as you have this arrangement, then these derivations become valid again. Therefore, when you have the line-to-line fault, it doesn't matter where the line-to-line fault happens. You can always turn it around so that you can obtain this kind of circuit again. And then you can use the equations that you have derived here again, yeah, for that kind of circuit. And then we look into the double line to ground fault. So let's consider that the double line to ground fault now is affecting phase B and phase C. In the double line to ground fault, they become short circuit instead of the impedance in between them. Now the short circuit is connected to the ground like this through the fault impedance like this. So in such a circuit arrangement, we say that VB and VC is now equal to each other, and they are further equals to IB plus IC multiplied ZF, such as like this. And then IA is open circuit, therefore it is 0. And from our symmetrical component analysis, we know that IA is equals to IA 0, 1, and 2 sum up together. All right, and they're equals to 0. And from our symmetrical component analysis, we also know this one. VB is basically equals to VA0 plus A squared VA1 plus A VA2. So this is actually VB1, yeah? A squared VA1 is actually equals to VB1. A VA2 is actually equals to VB2. And this is our positive sequence expressions for VB and VC. And because VB equals to VC, we can go ahead and take these long expressions equals to this. Then we will get these expressions, VA1 equals to VA2. Furthermore, we know that VB is equals to ZFIB plus IC. And we also know that from our symmetrical component analysis, IB is equals to this, and IC is equals to this due to the positive sequence order. And then we can substitute the expressions of IB and IC into here. It will look like this. And then if you simplify it, then it will look like this. Therefore, VB is equals to this. So VB is equals to this because VA1 and VA2 is equal to each other. We can take these expressions, apply into here. As you take these expressions and apply into here, VB will simplify, become these expressions. And from our previous derivation, VB is also equals to this. Therefore, this and this are equal to each other, such as like this. And this can be further simplified into this form. And from here, we can rearrange the equations by taking 3ZF over the other side of the equations, and we get IA0 equals to this. And then we can take this expression, put it inside here, okay? And then we solve for IA2. And then IA2 will become like this in terms of IA1. And then after we get IA0 and IA2, we substitute back into this, and then we will get IA1 in terms of just voltage and also the impedance. So the questions of if the fault happened now at the other two phases, is the derivation still valid? The answer is yes. You simply has to turn the three-phase system around until you get this arrangement again. All right. So with the derivations of the unbalanced fault equations, we are now ready to apply them if there is a fault happen in this 3-bus network. And let's assume that the fault now is happening at bus 3 over here. So the fault can be the 3-phase balance fault. It could be the single line to ground fault at bus 3. It could be a line to line fault, or it could be the double line to ground fault at bus 3. And then you are also given this data sheet which show us the impedance value for 0, positive and negative sequence of all these components, which is the generator, transformer, and also the lines. And we are also given that the generator neutral is further connected to the ground, okay, through 0.25 per unit impedance. And this value is useful for the zero sequence circuit later on. And notice that the impedance value for the positive sequence and the negative sequence, they are all equal to each other. And this is true for most of the time, but not necessarily, yeah. And of course, in the zero sequence impedance, it is definitely different from the positive and negative sequence impedance value. And the data sheet is repeated over here for convenience. And I'm also putting in the zero sequence circuits based on the connection diagram of the transformer over here for easy reference, which we will use later on. And we will come back to this later. When we have a fault happening at bus 3, we want to look into the network from bus 3 and then simplify the connections of the network. And because the impedance value at the positive and the negative sequence are the same, the positive and the negative sequence network are the same as well. So when we convert the network into the positive sequence or the negative sequence network, the first thing we do is we want to determine the R Thevenin of the network by looking into bus 3. And when we do that, we switch off the active sources such as the generators and also the transformer. So when we switch them off, they become short circuit, and we replace them with the positive or the negative sequence impedance. And the positive or the negative sequence impedance of the generator is given to us as 0.15. And the positive or negative sequence impedance of the transformer is given to us as 0.1, such as like this. And then we can go ahead and simplify this circuit into this, and then we can calculate what is the equivalence impedance connected to bus 3, and then we will get this value. So this value is the equivalence impedance of the network looking through bus 3. And this is what we call the Z331 or Z332, yeah, because this is applicable for both positive and negative sequence network. When we determine the zero sequence network, we also want to switch off our active sources. And as you switch off the active sources, you replace them with their zero sequence impedance. So the generators will become 0.05 because the zero sequence impedance of the generator is 0.05. But when you do that, you also have to add in additional 0.25. The 0.25J over here is the neutral impedance of the generator connected to ground, which is only applicable when we want to analyze our zero sequence network. As for the transformer, then we have to refer to this connection diagram. Recall that the transformer on this side just now is YY connected and both have neutral connected to the ground as such. And on this side of the transformer, it is delta on the primary side and Y on the secondary side. And then the Y has the neutral connected to ground, such as like this. So in this arrangement of transformer, it is easy. When you have both YY and their neutrals are connected to the ground, we simply connect the primary and the secondary through their zero sequence impedance, which is also 0.1, such as like this. But when you have a Y delta connections, the portions or the side of the transformer with the Y connections has to be connected to the ground, leaving the other side open circuit, and the impedance here is the zero sequence. So in this side of the transformer, the Y is over here in the secondary side, and the delta is in the primary side. So the secondary side is connected to the ground like this, okay, such as like this, through the zero sequence impedance of the transformer, leaving the secondary side or open circuit, such as like this. So to analyze and to simplify this circuit, we can simply ignore this part of the network because this is now open circuit. Okay? It's not connected to the network anymore. So we go ahead and simplify this network. It will look like this, and then we will get the equivalence impedance connected to bus 3 as this value of 0.35J. So we call this Z330. So with the derivations of the Z330, 1, and 2, we are now ready to determine the fault current, okay, at bus 3 for balance, 3-phase fault, single line to ground fault, line to line fault, and also the double line to line fault. So for the balance 3-phase fault, we know that the fault current is given to us as these equations. And we simply apply these equations. And when we apply this equation, notice that the impedance value that is taken into the balance 3-phase fault calculation is Z331. Yeah, it's not Z332, and it is not Z330. And this is the equations that we have derived for the single line to ground fault. And then you can go ahead and substitute the impedance for the positive, negative, zero sequence. And this is the fault impedance. And these three values we have derived over here. Yeah. And you can substitute there and then determine what is the value for I30, 1, and 2. And then you can determine what is the phase current through the phase and symmetrical current relationship. Similarly to the line-to-line fault, this is the equations that we have derived, and this is the relationship that we have established earlier on. And then we can also easily substitute the values of the impedance value and determine what is the symmetrical current. And from there, we can determine what is the phase current. And the same process is repeated over here in the double line-to-line fault. You substitute the impedance value inside and then determine the symmetrical currents and then convert them to the phase current, such as like this. So this is the end of the final part of the unbalanced fault analysis. And I hope you're able to follow until here so far. If you have any questions, feel free to drop me a message, and looking forward to your questions. Thank you for listening.